In this session, we will look at a decision problem that has been stated in words and structure it as a mathematical formulation, more specifically as a linear programming problem. So let's look at the word problem and see what it says. This is the Riser Sports Product Mix problem. This is a company which is producing two kinds of footballs, the All-Pro football and the college football. In order to manufacture a football, they need to use three processes: the cutting and dyeing, sewing, and inspection and packaging. Now, the other information that we have here is how much time do these two types of footballs take in each one of the three processes. So, for example, in cutting and dyeing, the All-Pro takes 12 minutes, while the college footballs take 6 minutes. And similarly, in sewing, the All-Pro takes 9 minutes and the college football takes 15 minutes. And in inspection and packaging, it's 6 minutes each. We also know that the total capacity in cutting and dyeing is 20,400 minutes, in sewing is 25,200 minutes, and in inspection and packaging, it is 12,000 minutes. The maximum production limits are also known. We cannot produce any more than 2,000 of all the All-Pro footballs and 2,000 of the college footballs. The profit per unit from the All-Pro footballs is 50, while from the college footballs is 40. So that is what then we know as the problem. Now, what we want to decide is how many All-Pro footballs should we make and how many college footballs should we make in order to maximize our total profit. Now, even for this small problem, just with the numbers that we have, it would be really hard to be able to just come up with a solution just like that, looking at the information that is given to us. So therefore, in these kinds of cases, and you can imagine that you could have, for example, 50 products, and you could have many more processes that you need to use in order to manufacture something. So maybe 10 processes or 20 processes, etc. So trying to make these decisions then becomes difficult just by observation, and therefore we can formulate them as mathematical programming problems. So let's go ahead and think about what we need to do if we do want to structure this as a mathematical programming problem or a linear programming problem. For any mathematical programming problem, we have three ingredients, or we will need three ingredients. What are the decisions to be made is the first thing that we need to define the decision variables. Then we need to think about what are the conditions to be met. And this is called specifying the constraints. And the last thing then we want to specify is what will help us decide what's the best decision for us. And that is specifying the objective. So let's do this. Let's go back to our problem and do all of these three things in the context of our given problem. What is it that we want to decide? We want to know how many All-Pro footballs to make and how many college footballs to make. So let's define the decision variables. We can say, let A be the number of All-Pro footballs to be produced, and let C be the number of college footballs to be produced. So that's the first thing that we've done. We've defined the decision variables. Let's go ahead now and think about the constraints. What would the constraints look like? So let's say in cutting and dyeing department, if you're making A All-Pro footballs and each All-Pro football is taking you 12 minutes, then in order to make a total of A of them, it will take 12 A minutes. Similarly, for the college footballs in cutting and dyeing, each college football is taking 6 minutes, and therefore making C of them will take 6 C minutes. So let's write that down. Each All-Pro football takes 12 minutes, and therefore A All-Pro footballs will take 12 A minutes. Similarly, each college football takes 6 minutes, and therefore C college footballs will take 6 C minutes. So therefore, the total amount of time that manufacturing these footballs will take in cutting and dyeing is 12A plus 6C. Now, since the capacity is only 20,400 minutes, then we must ensure that 12A plus 6C is less than or equal to 20,400. So that's then for us constraint number 1. Now, similarly, in the sewing department, since all pro footballs take 9 minutes and we are making A of them, the total time required will be 9A for the all pro footballs. And for the college football, since each one of them takes 15 minutes and we are making C of them, we will require 15C minutes. The total will then be 9A plus 15C, which then has to be less than or equal to 25,200. Similarly, 6A is the time we will take to make all pro footballs from the inspection and packaging department, and the time the college footballs will take is 6C. That has to be less than or equal to 12,000. 6A plus 6C has to be less than or equal to 12,000. So then here are the constraints that we have. That's the first constraint for cutting and dyeing. Here is the second constraint for sewing. And here is the third constraint for inspection and packaging. Now, do we have other constraints? Well, yes, we do, because the maximum production does not allow us to make any more than 2,000 footballs. So that is also a constraint. And similarly, the maximum production of college footballs is also 2,000. So then let's add those constraints to the above three. So A should be less than or equal to 2,000. That's our fourth constraint. And C should be less than or equal to 2,000. That's our fifth constraint. Now, there is another set of constraints that we always add for linear programming problems, which says that A and C cannot be negative, or else A and C have to be greater than or equal to 0 or non-negative. The reason for this, of course, over here is quite clear, because we are not going to be making negative numbers of footballs. So it's quite obvious that A and C will be greater than or equal to 0. However, this is a requirement for the algorithm itself, and we will look at that later.